So you guys saw what is mutual induction, right? Now we'll start with coefficient of mutual induction. See, now the similar way what we did for coefficient of self-induction. Okay, so you have a primary in which which is connected to the source. A current is flowing through it. So you have magnetic flux phi, which is directly proportional to the current I. Okay, so you have phi is equal to m into I, where m is what we call as the coefficient of mutual induction. Okay, so now you have phi is equal to m into I. Now remember, very important point here is m depends on both the coils. It's not just one coil, because here there are two coils which are acting in the particular circuit, right? So primary and the secondary. So now again the induced EMF and all those things will come here. So we have the induced EMF E is equal to, so d phi by dt, correct? So Faraday's law. So in place of phi, what do you put? You put it as m into I. So E is equal to d by dt of m into I. M is a constant, you take it outside. So you get E is equal to m di by dt. Okay. So here, using the induced EMF, we can define the coefficient of mutual induction. So we get m is equal to E divided by di by dt. So if di by dt is, let's say, 1 ampere per second, then we have E is equal to m, correct? Or m is equal to E basically. So now here, suppose if we are sending, let's say, 1 ampere of current in 1 second, then the induced voltage is nothing but the mutual inductance between the two coils. Okay, so mathematically, if you are trying to define, then you have m is equal to E divided by di by dt. So the proper definition becomes the coefficient of mutual induction or inductance is equal to the induced EMF when a current of 1 ampere passes through the circuit in 1 second. Okay, so this is how we define the coefficient of mutual induction.